All right, got one question by email, and this is considering organic problem 51. So it's asking you to assign the chemical shifts here. Let's see, and we're going to draw this out. This is carboxylic acid. B, E, C, D. Oh, hello. Just give me 1 minute just to get her a chair. I'll be right back. All right, so you're given a range of shifts. So you're given A, I'm sorry, 1.6, 4.0, 7.5, 8.2, and 12.0. So the easiest ones to assign are always the extremes. So oxygen is far more electronegative than carbon. This is a carboxylic acid, as the name implies. The hydrogen is quite labile. So your acid here is going to fall down here in the, so your E here is definitely going to be the 12.0. And if you look at, still need to load them up, tables of common NMR chemical shifts, that's definitely one that shows a lot of carboxylic acids, all sit down here at about 12. B is going to be your most protected. It's got the 3 hydrogens on the methyl group. So now you're left to organize the 4, 7.5, and 8.2. So you're going to expect the A here to be the most deshielded because it's closest to the most deshielded hydrogen. And on top of that, as we start working our way out, we should expect D and E. So if I start making these assignments here, let's see if I'm right. B is the most shielded. A, D, C. Make sure I enter that in right. B. Saying I'm wrong, but let me check to see what it says the solution actually is. So for those of you who keep getting this question wrong, you have done it correctly. The key is incorrect. So I'll show it to you on my end here. So if we switch to the desktop and you look at the initial problem statement, you get C, D, A, B, E. That's what's drawn behind me here. If you look, they're actually flipped in the key. So A is still that proton, but it's saying E now is the CH3 group, which is really B. And C is really this hydrogen here off the carboxylic acid, and D is this hydrogen here, so that one's still the same. And B is now become what C was. So if you're curious why you're getting the wrong answer, it's because the key is they actually have a different key. They have a different problem for the key. So let me send a comment to connect. That's actually really pretty funny. But yeah, if you look at the key, it's saying correct assignments, and their hydrogens are labeled differently in the solution than they are in the starting. So you would inherently get this one wrong just by merit of the fact that they got them mislabeled. And the weird thing is, it actually does agree with what I've got up here if you work it out. So this is number 51. That's so funny. But yeah, the top figure, which is the actual problem statement, and the bottom figure, which is the key, are actually two different problems. Not the first time they've done this to me. NMR to problem from the discussion board. There are actually 4 live streams from last week where I went over the NMR problem, so I'm going to redirect you to those. So those have been done many, many, many times. Page 59 of the test packet. Not in the description. So it depends on the NMR. So for carbon-13 NMR, typically what happens is they drop the singlets because they're all singlets. It's only in the proton NMR, that 1H NMR, do you see things like quartet, singlet, and triplets. So occasionally you'll see it. I try to be very good about labeling it in all the packets, but if you're like looking through problems, some problems just straight up don't label them. They expect you to interpret from the signal. I take issue with that because particularly if you get like something that has a multiplet in it, it gets really hard to figure out what the actual splitting pattern is. On top of that, you may have a multiplet, but because the signal is so weak, you don't necessarily see the other parts of it. Other questions out there? '58, '59 on the test packet. All right, so this 58, 59 is kind of representative of what you would expect to see, particularly as we start getting much, much later into the semester. So from our carbon-13 NMR, switch to a different pen, this one's starting to die on me. We see that we've got 4 functional groups in a 1 to 1 to 1 to 1 ratio. And we've got chemical shifts of 210, 38, 39, and these are all pretty shielded. So if you looked at tables of chemical shifts, this is probably looking at the alpha group. That's something super acidic. If we look at the 1H NMR, we've got 3 functional groups with hydrogens. And chemical shifts 2.45, 2.15, 1.05, and these are all pretty consistent with alkanes. And we've got one that sees 3. We've got one that sees 2, and then we've got one that's isolated. And the one that sees 3, where are you? Oh, we've got areas of 3, 3, I'm sorry, 1, this sees 2, and this sees 3. I'm sorry, this has 3. We have 2 that see 3, 3 that see 2, and 3 that are by themselves. All right, from the EI mass spectrometry, we're looking at an atomic weight of about, looks like 72 AMUs. And from the IR spectrum, we definitely have this. Yeah, we'll go over the chirality one next. If we look at the IR spectrum, it looks mostly like we've got alkanes. But we've also got something there that's in pretty deshielded. That peak about 16, 1700, I'm thinking that's an ether. So we've got, this looks like a methyl group. So an isolated CHA group that doesn't have any adjacent hydrogens. This here looks like an ethyl group. And the reason why I say it looks like an ethyl group is that we've got 2 that see 3 and 3 that see 2. So 2 that see 3 and 3 that see 2. That would be my assumption there to say that it's an ethyl group. We know that we've got 4 carbons in this. So 1, 2, 3. Ooh, I bet it's not either, but it's a carbonyl. That would make a lot more sense. So there's 1, 2, 3 hydrogens. And those would be consistent with what you'd expect to see for alkyl groups. That would be consistent with alkyl groups. The question is, where do we get this 4th carbon that's super deshielded and apparently doesn't have any hydrogens on it? So apparently we've got a carbon with a CH3 group hanging off of it, an ethyl group hanging off of it, and somehow or another this doesn't have hydrogen, so we need to basically bond it up. So let's count up the weight so far. We've got 17 plus 12 plus 14 plus 17. So 34, 48. No, that's not right. Yeah. 34, 46. Something's off in my math. Test format's going to be 10 multiple choice questions, and I think there's like 5 free response. So right now we got 60 AMUs with what's written here. And I think I read that figure wrong. So we have 4 carbons, weighs 70 AMUs, and so far we've got 48 plus the 8. 6, 8 should give me 56. Oh, I've had it wrong. That's my problem. So right now we're at 56. So we need to somehow get up to 72, and we need to get rid of all the hydrogens on the carbon. So the easiest way for me to do it is to say, well, let's pretend it's an oxygen. So if we add an oxygen, that'll get us to 72 AMUs. That would be consistent with a heavily deshielded carbon, and that would reproduce our spectrum. Trying to do a quick and dirty add up on this. So carbon weighs 12 plus 3, that should actually be 15, not 17. And that's where my math was off. And that's 14 and that's 12. So actually I wrote 17, that's true for nitrogen with 3 hydrogens. For carbon with 3 hydrogens, it's 15. So it's 30, 56. So that's where my mistake was. So if we compared the IR, the atomic mass. So if we compare the IR, we get the carbonyl bending mode there. That's what you're seeing at about 1800 or 1700 wave numbers. Again, nothing like this is going to be on the first exam. This is just to kind of give you a feel of how this type of information is used. And this is definitely a problem where you're kind of walking in blindly. There's no first guesses here. This is much harder than anything you will be doing for the rest of the semester. But it is to give you a feel for like how these types of problems are worked. So I counted up my number of carbons, I counted up my number of hydrogens, I figured out what the weight was, and anything that remained was going to be picked up from the IR. I used the chemical shifts to estimate probably what the groups are. These are definitely consistent with alkyl groups. These are consistent with alkyl groups. That's a lot more consistent with the carbonyl. And then from there, kind of guess and test. But again, ideally what you would do is you have something where you said, I ran this reaction, and I ran it against chromic acid. What did I get? Well, I'd expect this to be a ketone when I ran it, but there's other things that chromic acid can do, so you're kind of verifying your answer. But yeah, you're definitely not going to see like anything like that on this test. Second problem on chirality, page 37 in the packet. Yeah, you kind of can, and this is kind of the issue with doing this blindly. If you don't have a good first guess, you're kind of having to estimate where it can be, and you can definitely find like carboxylic acids and carbonyls kind of give roughly the same chemical shifts. So it doesn't do you a lot of good. You can also see like the carbons and the hydrogens didn't really shift that much away from the ideal range despite being bound to a carbonyl carbon. So I'm not a huge fan of using the estimates. Again, I would much rather have a first guess. So the one page 37, I've actually got a couple. So this one, and this one. So if we start with the top one, hydrogen's in the back, and if we look at what else is, so hydrogen's going to be the fourth priority. If you look what's in front of it, we've got 3 carbons, so we need to write what's beside them. So we got hydrogen, hydrogen, hydrogen. Oh, sorry, there's one more. This is a carbon, hydrogen, hydrogen, and this is a carbon, hydrogen, hydrogen. So first point of difference here is a hydrogen versus carbon versus carbon. This makes this one priority 3. And then the shortcut for alkanes, whoever branches first is the higher atomic number, or has the higher priority. Whoever terminates first is the lowest. So if we go 1, 2, this terminates first, so this is the second highest priority, and this is the highest priority. Now, luckily the hydrogens point it to the back, so if we can just look at it as is. This is how we would expect to see it if we were to build the model and look at it with the lowest priority group behind it. This is counterclockwise, so this is the S conformation. Here we've got 2 groups, so we need to look at them individually. So if we look at it from this hydrogen's point of view, from this one's point of view, we have one hydrogen going back, that's the lowest priority. If we look at this one, we got a carbon, carbon, and a carbon. This carbon is bound to 3 hydrogens. This carbon is bound to a carbon and 2 hydrogens. This carbon is bound to a fluorine, a carbon, and a hydrogen. So in terms of priority, the fluorine is going to win out, followed by the carbon, followed by the hydrogen. So we have 1, 2, 3 in terms of our priorities. And again, since we have this hydrogen going back, we can just look at the diagram. If the hydrogen was a wedge or this was a dash, we'd have to flip what we're doing. At that point, I would say just build the model. It'd be a lot easier. This goes 1, 2, 3. This is clockwise, so this is an R center. Now if we do the same thing for the fluorine, hydrogen goes back, it's the lowest priority. Fluorine weighs more than both carbons, so this is the highest priority. And since this branches first, this direction will end up being the higher priority. This branches last, so it's the lower priority. So we have 1, 2, 3. This is counterclockwise because the hydrogen's pointed back. So this would be an S. So I would say this is an RS center. Can we go over one with Fisher projection? Yes. So if we go to page 19, and these are ones where the Fisher projection will be drawn out in the key. And the problem statement does tell you if it's RS, so you can compare your answer to what's written there. So for the IR, at this point, we're not analyzing spectra. We're more just trying to understand what the technique is. So when we start getting to like the alkanes, that's when we'll bring back up the IR and say like, okay, for the IRs, this is what you're expecting to see. When we do alkyl halides, we'll do the same thing and say, okay, in the IR, this is the peak that you'd expect to see. For alcohols, this is the peak you expect to see. So we can do IR, but the thing is that IR kind of needs a context. Like you need to know what functional groups you're looking for. So we always knew like there's going to be a CH3, CH2, CH stretching modes. Those sp3 hybridized carbons are all there. The bigger thing is we're looking for functional groups unique to our molecule. And so I think right now the bigger thing is just understanding what the technique is and what it can tell you. And then as we start getting into the different functional groups, we're going to start coming back to the IR and the NMR and saying this is what you'd expect to see. All right, so page 19, first one. If you look at the key, it gives you that the Fisher projection, let's see here, is this. And you're told that this is 2S, 3S, 3 bromo, 2 butanol. And so it's automatically telling you what the numbering is. So this is the third carbon, and this is the second carbon. So we know what the answer needs to be. So the question is, how do we get to it? So if we look at this one, so let's start with the alcohol. Hydrogen's the lowest priority. The oxygen here is going to be the highest priority, and this leaves us with a CH3 and this carbon bound to 3 hydrogens. This is carbon bound to a bromine, a CH3, and a hydrogen. So this is going to be the lowest priority, and this one's going to be the highest. So now we've got our projection. We got 1, 4, 2, 3. And this is for the top one. So we know it's supposed to be S, and the way we can, but let's prove it. Let's not actually accept it as S. From the Fisher projection, the easiest thing to do, swap the lowest group, the 4, with the highest group. So we're going to flip the oxygen to the other side, and then we're going to erase the lower priority group. Watch this assignment be wrong. And that's actually clockwise. That's probably supposed to be 2R. Unless I drew the Fisher projection wrong, which wouldn't surprise me. So I'm actually getting 2R, not 3S. So let's see if I got it right for the bottom one. So now if we do the bottom one. Bromine's highest, hydrogen's lowest, and this has connected the oxygen, so this is going to be 2, This one's going to be 3. And if we draw it again, we've got 1, 4, 2, 3. So if we swap the 1 and the 4 with whatever's lowest, with whatever's opposite, we'll get this. And if we draw it, that's also clockwise. I'm thinking that this, I've actually flipped my Fisher projection. Yeah, I flipped the Fisher projection. That's the problem. That's why I keep getting the wrong answer. Let me build this really quick. No, that's built correctly. I think they are, and the answer just flipped on that figure. Go figure. That's 1, 2, 3. That's definitely R. Yeah, they're just flipping that one. Okay, regardless, this is how you would do it for a Fisher projection. Number them, draw the cross off to the side. Whatever's opposite the lowest group, they just happen to be 1s in this case, but you would just flip whatever the lowest priority group is with whatever group's opposite, erase the lowest priority group, and then see which way it goes. In case I didn't answer, are there assumptions from the chart? Like based on where it should be? Yes. With all IR and all NMR, and NMR in particular, they give a common range. They can definitely step out of that range. Generally, they sit in that range, but you can definitely find exceptions. Particularly with the alkane range, if you start throwing halogens in there, they start going all over the place. Or if you happen to put it next to like benzene rings and things like that, they can start going all over the place. Other questions out there? All right, I'm going to pause the screen. I'm just running over to grab my flash drive. I'll be right back. But again, if you have questions, please feel free to post in the chat. I'm still here. All right, going to go over hybridization. So, and the questions are specifically for pages 10 and 11. So let's do page 11. That's actually got the better variety of questions on it. So with hybridization, it depends on who taught you, but the way I teach it is to do the AXE and then drop into the AY. And English, I'll get to your question in just a minute. So the AXE, there's a number on X, so we'll call that A, and there's a number at E, which we'll call B. And the AY is just the A plus the B. So if we have AY2, this is SP hybridized. If we have AY3, it's SP2 hybridized. And if we have AY4, it's SP3 hybridized. So what we have to figure out about our atom are the X's and the E's. So the X is the number of atoms that it's bound to. Not the number of bonds it shares with them, just the number of atoms it's bound to. And E is the number of lone pairs. So if we look at the nitrogen here, nitrogen has 3 atoms bound to it, hydrogen, hydrogen, and carbon. So it's AX3, and has 1 lone pair, so it's E1. And that would make this AY4, which is SP3 hybridized. This carbon here has 4 atoms bound to it, 1, 2, 3, 4. So it's AX4, E0, there's no lone pairs, that makes it AY4. So this is an SP3 hybridized carbon. This carbon here has 3 atoms bound to it. So 1, 2, 3, so it's AX3, E0, no lone pairs on it, so that would make it SP2 hybridized. And now if we look at the oxygen has 1 atom bound to it and 2 lone pairs, so it's SP2 hybridized. So the reason why I teach the AY, you just have to memorize, particularly for organic, you'll have to memorize their 3 cases, AY2, AY3, and AY4. Chem 1, we do AY5, AY6. They're fiction. They don't actually do any of that. Actually, none of this happens either, but we still have to learn it. And so now that you have the hybridizations, you just describe, what we're describing with these hybridizations are what's called the sigma bond. It's the first bond between adjacent atoms. So hydrogen only has a 1s, so anything bound to a hydrogen is going to be a hydrogen 1s plus whatever it's binding to. So this is a hydrogen 1s bound to a nitrogen sp3. This bond here is a carbon sp3 bound to a nitrogen sp3, whereas the bonds between the carbons and the hydrogens are a carbon sp3 bound to a hydrogen 1s. This is a carbon sp3 bound to a carbon sp2. This is an oxygen sp2 bound to a carbon sp2, and that's where the parent goes from there. That probably is a mistake. Oxygen should be sp2. It probably was just copied and pasted from the carbon that was beside it, or that was down to the left of it. All right, so all the techniques you need to be familiar with. Carbon 13 and 1H NMR, and specifically you need to be able to identify peaks. So in the sense that if I give you a figure, it's like the discussion board. If you're given a figure, you need to be able to tell me which peak corresponds to which particular atom in that structure. You need to know IR, and this is just qualitative information. So we're not to the point yet where we're identifying like compounds. Yeah, you're welcome. We're not to the point where we're like trying to identify compounds from their IRs. We're just not there yet. But right now you're getting just familiar with what the technique can tell you. Polarimetry, definitely what you saw on the discussion board. I think some of you have been looking up the alpha D instead of calculating it. You really need to be much more comfortable with calculating it. But the definitely problems you see in the packets. If I give you a problem regarding polarimetry, can you tell me um, like what you expect, what the EE is, or what you expect the specific rotation to be? Mass spec. Big thing here is just the parent ion. So can you figure out what the parent ion is? Can you figure out how much the compound weighs? Can you resolve compounds based on their atomic weight? So very much what you see in the discussion packet, like if you've got a list of 4 compounds, which one is it probably? Let's see, what other techniques are on there? ESP. Again, kind of qualitative information and polarity. Can you identify the polar power of a molecule? How would you identify the polar power of a molecule? And actually with this course, the way we set it up, we consider the Fisher projections and the Newman projections part of these techniques. So for the Fisher projections, can you identify the chiral centers? Can you tell me if there are or there S? For the Newman projections, can you tell me based on the Newman projections which conformations are more stable? And the last one is the combustion. And there we're just looking for stability. Relative stability. Well, the nice thing about it, so if you have a racemic mixture, the alpha is 0. So racemic mixtures are what we would consider the trivial case. So in mathematics, the trivial case is where everything equals 0. I mean, that is truly an answer to the question. It just isn't a particularly useful one. So know that a racemic mixture does give you an alpha of 0, just so you don't waste your time trying to figure that out. But generally speaking, the problems are going to be a bit more involved than just a racemic mixture. Racemic mixture shouldn't have any optical rotation. And the racemic is going to start coming up a lot when we start talking about when we get to test 3, because we'll be looking at reactions that even on test 2, like when we start replacing hydrogens with halides, we can get racemic mixtures. You would only use that if you had an enantiomerically pure, so EE is 100%. So this is, what you're seeing is just kind of a special case. So if we have alpha equals, let's say we're working with the D enantiomer, L times C times EE over 100. If EE equals 100, then we just have alpha equals alpha D times L times C. And we're just down to two variables now to solve for. So if we want to know alpha D, that's just alpha over LC. Or if we want to know alpha, we just plug in all the numbers. But this formula here is just a special case of this formula here. You'll be given enthalpy. That's what you measure experimentally. We're definitely not in Chem 1 where you would have to figure it out from the Hess's law. You would just be given the delta H for the combustion of each one and asked, okay, based on this information, is A more stable, B more stable, or can you not tell? So very similar to what you see in the packets. The other thing to keep in mind with these packets, part of any course is review. And there is some review in these packets. So a good example of that is, where are you? So if you look at page 21 in the packets, define the following terms: Gibbs free energy, enthalpy, entropy, spontaneous, non-spontaneous, exothermic, endothermic. That's review. You're not going to get asked questions on that. But definitely, like, the questions that follow is like, okay, based on this combustion, what do you expect to see? The point of that page 21 is just to make sure you kind of remember this. When determining RS, if the lowest priority is a dashed line, do we still flip the group opposite? So if you're doing the Fisher projection gets rid of all those wedges and dashes. So the Fisher projection is done the same way every time. There is a way to do it directly from the drawing. So let's say we have alpha, beta, gamma, and delta. So if beta is the lowest, okay, so if alpha is the lowest, you reverse the R and the S. Whereas if delta, gamma, and beta are the lowest, you can read it as is. So what this says is that if, let's say alpha is a hydrogen, that would guarantee that it's the lowest. And we don't know about beta, delta, and gamma, but let's say that they follow the Greek alphabet. So this is, beta is 1, 2, 3. If we saw this, if we just drew this without the hydrogen, we'd say 1, 2, 3, this is counterclockwise, but because hydrogen is the lowest group and it's pointing at us, this would actually end up being, not S, be R. So if the hydrogen's on the wedge bond and you read the other groups and they go counterclockwise, they're R. If they go clockwise, they're S. For all other cases, so let's say hydrogen is down here, and you've got alpha, beta, and gamma. Alpha's 1, 2, 3. This reads as clockwise. When you erase the hydrogen, it's still going to read as clockwise. So that would be R. So you can definitely do it from the figure. I just don't advocate for it. I would say you either need to build the structure or build the Fisher projection, because there are assumptions built in with this that can kind of like get you off. But it's only if hydrogen is the highest do we kind of like get these rules flipped around. But if the lowest priority group is a dash, you can read it right off the structure. So generally speaking, we'll say hydrogen is because it's always lowest. If hydrogen has a dash, you can just read the groups as is. If they go clockwise, it's R. If they go counterclockwise, it's S. Only if it's in a wedge do you have to reverse that rule. Other questions? Yeah, if it's red, if it's dashed, it's automatically the way you would be looking at it if you had the model in your hand. And then there is a way to prove it with the hydrogen being down to the left or to the right. I've done it in a previous video. I'm pretty sure what I put up here is correct. Not 100% sure. I don't normally do it from the line bond drawing. I am trying to get better about being able to do it from the line bond drawing so I can explain it to students better. I understand the want and desire to be able to do it from the line bond drawing because it saves you the trouble of building the model, or it saves you the trouble of building the Fisher projection. But my worry with doing it directly from the line bond drawing is that you are inherently having to rearrange in space. Your model will never make a mistake. Your model, once it's built, is built. You can never like accidentally break bonds and you're taking a model and turning it. in your mind, you can definitely flip things around. Test 1 homework shit is due. So if you go to My Grades, it'll show you. That's odd. Why is it saying the test 1 material doesn't have a due date? How would you differentiate between relative and absolute configuration? I keep getting those two mixed up. So if you have a relative configuration, there's no wedges or dashes. If you have an absolute configuration, there's wedges and dashes. So the due date for the test 1 material is September 15th at midnight. So that's when you would have, that'll be after you take the exam. Now, you can always go from an absolute configuration to a relative configuration. You can't go back. So when you have an absolute configuration, you are specifying R and S, or you're specifying stereochemistry. There's two cases for this. So if you have, there are times where we don't care. So in particular, we can run a reaction with an alkane where we add HCl. And what we're actually going to end up with are both the R and the S configurations. So both of these statements are true, and we have to write them both. But let's say we're taking this reaction and we're following it up with an elimination reaction. For whatever reason, we decide to take it, make it, and then eliminate. So we go back to this conformation. Well, there's really no point in writing both, because even though your intermediates create stereoisomers, the stereoisomers are destroyed on subsequent reactions. So in that case, we would just write this to say that, yeah, we have both R and S, and there we're not going to designate which ones we have, because we're going to immediately destroy those chiral centers. But if you have a stereospecific reaction, so let's say this will be a reaction you get to learn later this semester. Hydrohalogenation. In this case, we have to specify that we got this product, because they never appear on the same side. So when you run this reaction, oxygen and chlorine get added on opposite sides of the double bond. We don't have a choice, we have to write this. So if we wrote this, what we're saying is that there's an equal probability of finding this is wedge and dash and this is wedge and dash. So in this case, we'd have all four enantiomers. In this case, we're saying we have a very specific stereo isomer. There's nothing else in there but this. Now, the other time you encounter stereoisomers when they're not needed, okay, well, I shouldn't say when they're not needed, just mostly like you wouldn't normally incorporate them, is when we look at the elimination reactions. Generally speaking, we wouldn't bother putting wedge dash on these hydrogens, because this is not a chiral center. But when we talk about this reaction, we'll talk about how there's actually a rule when we do the elimination. So this is tert butoxide. It will always attack the hydrogen that is on the opposite side of the chlorine. This is called antiperiplanar. So this wedge hydrogen doesn't get attacked, but this dash hydrogen does. And we need to draw the stereochemistry in here to designate that, yes, there are two different types of hydrogen, and only one really gets attacked, the other one gets left alone. And this will actually explain why, if you do, let's say you put a fluorine here on a chiral center, you will always get the isomer where the fluorine is on the same side as this methyl group. Let's say it was an ethyl group, so we can designate. You can prove, because of this relationship, you will only ever end up with one stereoisomer. But yeah, relative configurations, just there's no wedges or dashes, and it's because either we're assuming that we have a racemic mixture of all stereoisomers, or we're saying it honestly it just doesn't matter. And the latter shows up when we start running subsequent reactions. We might produce a racemic mixture of R and S, but we don't care because we're going to take that chiral center and eliminate it. The other case where you would have like an absolute versus a relative, if we're going to do mechanisms, which will start showing up for test 3, that's when we might need to start designating how these atoms are related to each other in space. Correct. So if you see wedge and dash, that's an absolute configuration. You are definitively saying that atom pops out of the page and that atom goes into the page. And again, there are cases where that does and doesn't matter. So if you have an achiral center, so if we have this molecule, this 2,2-dibromopropane, this is true. This is 100% true. But because this is chiral, we don't care. We can just write this. It doesn't matter that these are both wedged or dashed. 21 on the homework. No, you're welcome, Dia. Draw the line bond formula for the 5 isomeric C6H14 alkanes. So question is, how many rings and potential double bonds do we have? So if we had an ideal saturated alkane, we'd have 2 times 6 plus 2, that would be 14 hydrogens. So this is a saturated hydrocarbon. So there's no rings or double bonds. So since 2 times 6 plus 2 equals 14, we know that there's no rings, there's no bonds. So now we can start trying out iterations. Just can't get past 2. So always start with the easiest one, straight line. 1, 2, 3, 4, 5, 6. So there's your first option. Now let's take this methyl group and let's move it somewhere. So if we move it to the first one, this is unique, this is distinct. So if we take this methyl group and put it on the second carbon, we have now a 5-carbon ring with a methyl group hanging off. We can put it on the next one. And now we've got a unique one where there's kind of got this, I guess, umbrella shape. Now if we moved it to the third one, we wouldn't really get anywhere because that's just this one spun around 180 degrees. I'll see if I can figure out how to get to it. I know that, I think you click on the Teams link, it should take you to at least the chat. And from there, you should be able to download it from the chat. But honestly, I've never had to pull a recording off of Teams before. All right, so we're at 3. Let's clip another methyl group and let's put it over here. So now I've got these 3 methyl groups and this ethyl branch. Now I can take it and I can move it to the next one and I get this shape. And if I put the methyl group back on there, I'm back to where I started. So these would be your 5 isomerics. Linear, 1 branch, and 2 branches. Not what I clicked. So if you're in 4101, it looks like nobody actually recorded the meeting. I think someone tried, but I'm not seeing anything saved. If you're in 4136, if you go to the team in Teams and just click on the post, that should send you right to the recording. Yep. To try to go to the Teams channel itself, so if you just click on Teams and then find the channel, if you were in the afternoon, somebody definitely recorded that one. But the morning, I'm not seeing a recording. Yes, we're going to a different room. I still haven't gotten confirmation, so it's looking like Monday you're going to get an email telling you which room to go to for the exam. But I got an email this morning about scheduling, so there's optimism there that hopefully by the end of the day we're going to get a confirmation on what room we're taking in. I think right now we're looking at SD 228. So we do lab in building SC. SD is actually connected on the northwest corner of it, so they actually share the elevator. And SD, I think, is inside the building. It's an awful room to lecture in, but it's great for exams. Excuse me. As far as the Eisenhower questions go, they're just hard. So what you're going to see on the exam are the two simplest cases, because again, I don't want to get you kind of like bogged down and having to do all these iterations. But as I told Dia in a previous stream, there's no way to algorithmically do this. You just kind of have to like try and see how clever you're feeling that day. That's the interesting one. I don't know if they're gonna, if you can share the meeting. There we go. So I've sent you the link to the meeting. Oh wait, you can't access it because you're not in there. So I can't send you the link because it's you have to be a member of that team in order to be able to see it. Yeah, I can't share the link from 4136 with 4101, which makes sense. That's an issue of we are not supposed to confirm or deny if students are in our courses. It is at the bottom though. I am seeing a recording. It's saying you can't access it either. Okay, I can't email you the link. Oh yeah, you can definitely download it. I can't control once you download it. So if you go directly into MS Teams and you hit the Teams link and go to your section, I don't know why it says the meeting's still going on, but yeah, if you go to the bottom, so on the channel, on posts in general, you should see. How odd. Yeah, you're free to email it. Wow. All right, it is 12 o'clock, so I need to head out. We've got two more live streams, one Monday, one Tuesday. Organic folks, you're in here in mass. Your exam is Wednesday. I will try to get the email to you. If not today, definitely by Monday to let you know what room we're doing. I'm also going to try very hard to remember to post the tables that you're going to get access to for the exam. So, other than that, I will see y'all next week. I'm kind of in email contact. So for anyone who's in taking Chem 1, I'm going to try to be as much in email contact as I can. I know you're taking the exam this weekend. Email me if you're having technical issues. I will try to get back to you as soon as I can.